Okay. Problem 5.1. It's asking you if two adiabats can intersect, two reversible adiabats. So we are going to prove it using the contradiction route. So we assume, let's say, two adiabats, reversible adiabats are intersecting. AB is one of those adiabats and CA is another adiabat. So let's assume they are intersecting. Reversible adiabats are isentropic. So the entropy change along these two would be 0. And now I connect. So I am free to choose any point on B and C. That means B and C I am making arbitrary and connecting them in such a fashion that the path from B to C is isothermal reversible. Okay, and we are not making any assumptions up to this point. All right. So you can prove now the contradiction via several routes. So you can show that the entropy change from BC will not come out to be 0. So on the circular path, entropy change is non-zero. Entropy is a state function. Therefore, it violates the second law. Okay, because entropy is a state function by the second law. Other option is that there is a cyclic process happening. So statement 1A, you can try to attempt. Statement 1A says in a cyclic process, all heat absorbed cannot be converted to work. So let us see if we can prove it otherwise here. If something else is happening, that means if all the heat absorbed in a cyclic process is getting converted to work, again it's a violation of statement 1A of the second law. So the area enclosed by this curve, all steps are reversible. So I can use PDV as my work. You can clearly see the area enclosed is not 0. Okay. If I apply the first law on the entire cyclic process, so delta U is 0. W we have just proven is not 0. Therefore, Q is not 0 either. And further, you can see Q is equal to W. That means in a cyclic process, all of the work is getting converted to, all of the heat absorbed is getting converted to work. Again, you can indeed show that Q in this case would be heat absorbed. So those are the various different routes by which you can prove that two reversible adiabats will not intersect. Okay. Any query on this? One error which I made in a previous class. I asked to compare the work in a reversible versus an irreversible adiabatic process between same endpoints. So it is not possible to have a reversible and irreversible process between same endpoints. Reversible adiabatic versus irreversible adiabatic. So A and B are two endpoints. A is connected by reversible process, and in some other case connected by an irreversible process. So your answer for entropy change, if I use the reversible adiabatic, it would be 0. Versus if I say that it was the irreversible process I am focusing on, irreversible adiabatic, it will not be 0. So again, that's a contradiction which is not possible. Okay. So that question is in a way not getting started. You cannot have reversible adiabatic, irreversible adiabatic between same endpoints. So in some sense, it is related to what we are seeing in 5.1. Now, in general, if you want to calculate entropy changes in any process, and that is fully general when you don't know anything about what is happening. Okay, so starting point has to be which is this. So this is general, not specific to a given problem. But anytime when you want to calculate entropy change, you can always start here. And now your would be to an extent something which we have discussed in chapter 3 also. Okay, chapter 3, even chapter 2, chapter 4. So in all of those cases, we have about how to calculate heat effects, how to calculate Q, okay, along a reversible path. So once you start with this definition, you can attempt to obtain entropy change for any arbitrary process, any arbitrary species. So let us take an example. And because we have only worked with ideal gas when it concerns enthalpy entropy changes, so for now, I will focus on ideal gas as a working fluid. Once we go to the next chapter, chapter 6, we will be able to go to real gases also. So I start with the first law for a mechanically reversible process. So this dq reversible we have seen even if you have a mechanically reversible process versus a fully reversible process, dq is same. So therefore I'm writing dq as dq reversible. I'm going to use h instead of u, and that is just because of the convenience of the final set of equations we are getting. Okay, so there is no other reason. You could have worked with u also. Okay, so I make that substitution, and this is the new equation I get. If your process is at constant v, you will use the first one. If your process is at constant p, you might find the second one to be more convenient in the sense that the reversible heat transfer is related to enthalpy changes at constant pressure is related to internal energy changes at constant volume. Okay, so that is why we have two options here. So now let us look at constant volume case. Work is 0, and we have an expression for the internal energy change, which is CVDT. Okay, so from here, now you can write down the entropy change in going from T1 to T2 as this integral. Further, if CV is constant, you can simplify it more. Okay, so now if you look up the derivation route, right, I have wrote this equation by taking some assumptions. Okay, so what are the assumptions I have taken in deriving this equation? Anyone? What assumptions have gone in? There is no penalty for speaking up.
Ideal gases.
I have not so far, right?
Sir, du is equals. Acha, right.
Mechanical reversible at constant volume.
Mechanical reversible constant volume. Okay. Now, using this second route, at constant pressure, dq you can write in terms of enthalpy changes. Okay. And fully general, let's say the last case where I just start at first law and mechanically reversible. For now, I will give you the expression for ideal gas, because for ideal gas, we have an equation of state available, which will be required. Okay. So what you see here is for this part, V as a function of P and T, I am going to use the ideal gas equation of state. Once we learn how to calculate enthalpy changes, internal energy changes for real gases, we will be able to use the same route for real gases also. Okay. But for now, let us focus just on ideal gas. Okay. So now for the fully general case, okay, so I'm not saying constant volume, constant pressure, nothing. So all I'm going to do is substitute in that initial equation dq in terms of enthalpy changes and the vdp term. Okay. And the reason I am doing that is going to be clear here, that I get an equation where everything on the right hand side is available for me, because I know how the specific heat capacity of an ideal gas depends on temperature. Okay. So this is the fully general form. In all three, so let us forget the specific details. Now let's say I have changed from point A to point B along some arbitrary reversible path, or sorry, irreversible path. So it could be reversible or irreversible, irreversible or reversible. So all of my derivation has been mechanically reversible, or I have made some other assumptions also. So now I am saying maybe the process is not mechanically reversible, which is many times the reality. Can I use the equations for entropy change I have given here? Let us focus on the boxed equation, which is the most general, which doesn't say constant volume, constant pressure, constant temperature, nothing. So that is a fully general otherwise. Except I derived it by saying I have a mechanically reversible process. So now can I use this boxed equation for an arbitrary irreversible process also?
So the endpoints are same, right?
Yes, yes, yes. So now we are saying, so we are actually not saying it's, we have a single path. I'm not right now talking about a reversible path. All I am saying is I have a process from point A to point B involving an ideal gas. I want to calculate the entropy change. Can I use the boxed equation?
So this dp by p would vary with different paths, right? I guess we can't use this.
So all the terms right hand side are state functions. Specific heat capacity in general is not, but once we define Cp, Cv the way we defined, they are state functions also. So everything on the right hand side is a state. That means path independent. That is the meaning of a state function. So even though I have derived this equation by assuming a mechanically reversible path, Boxed equation is valid for an irreversible process also, as long as I'm talking about state properties. Okay. If I ask you about Q and W along this path dependent. However, state property changes by definition depend only on the state. Not matter now whether I derived it via reversible. So I am focusing on the end result, the boxed equation. In the boxed equation, everything on the right hand side is a state function, path independent, for any arbitrary case. Okay, so this boxed equation would be equally valid for an irreversible process if you want to calculate entropy change from A to B. And the reason being, you can connect A and B via a hypothetical reversible path. And now I can calculate entropy change from A to B along the green path. And because entropy is a state function, so entropy change from A to B calculated from the green or the blue curve is going to be same. And therefore, the boxed equation is valid for any irreversible path also. Okay. So now let us try to solve some problems using this. And any query?
No, sir.
So 5.8 will make use of one of these equations. Focusing on entropy change for water. When its temperature is being increased at constant volume. So we have already derived the relevant equation for this. So I directly use it. Further in the problem statement, they say you can take Cv for the given range to be constant. So I get a simple expression. Okay. Now for the reservoir, so they want us to calculate the total entropy change. Okay. So the way this process is happening is by bringing water in contact with the reservoir at high temperature, either in one step or in multiple steps. Calculate the entropy change of reservoir also. In the lecture class, it has been mentioned that for the reservoir, you can assume the entropy change to be reversible always. And the main reason for that is there are no temperature gradients in the reservoir. So since there are no temperature gradients in the reservoir, I can take the process to be reversible on the reservoir side always. Okay. And now in this case, because the reservoir is on constant temperature, is at constant temperature, so the integration would still simply give me minus q by t. Okay. This q we have already obtained. This is the q for the system. Okay. Cv they are saying we can take constant. So this is what I will get for the reservoir side. Okay. Now there are several cases given. In case A, you have a single reservoir at 100 degrees Celsius and the system is taken from 0 to 100. In case B, you first take the system to 50 degrees Celsius via reservoir 1 contact. Then you change the reservoir temperature 100 degrees Celsius and you take the system from 50 to 100. Okay. Case C, you do it fully reversibly. Let's not use the word fully. You do it reversibly. That means if you look at A and B, using an infinite number of reservoirs with infinitesimally small increments in temperature. Okay. So reservoir 1 will be at 0 degrees Celsius plus delta T. Reservoir 2 at 2 delta T. And you do this up to infinity till you obtain the last reservoir at 100 degrees. Okay, so that is what we mean by infinite steps. Infinite small steps give you a finite change. Okay, so that's what we are doing here in part C. So what is the total entropy change in part C? Positive, negative, zero. You can talk to each other, rise from your morning sleep and try to give the answer. Okay, so move to next. You can calculate for A, B, and C and check what you get. So 5.31 refers to what are known as HVAC systems, which are typically found to be economical if you are looking at a very large building, which is centrally being maintained. Okay, so H refers to heating, V to ventilation, and AC to air conditioning. So those are the three aspects of HVAC systems. So they allow you integration of various different aspects. Okay, in thermodynamics, you will see here that once you are allowed to integrate different, you can improve the efficiency very, very drastically. Okay. So here they are giving you a very simple example. In a house, by providing heat from a furnace, and let's say the requirement of house, that means the heat input to the house is fixed, it is some value Q. This is being done essentially irreversibly. So this is very similar to the example of putting a rod between two hot objects, or a hot and a cold object. Rather than putting a Carnot engine, which gives you full reversible transfer of heat, you are putting just a conducting rod between two, which gives you fully irreversible transfer of heat. Okay, so in doing this, clearly see no moving parts, nothing. So the net work output is zero. thermodynamic efficiency in some sense is zero. Okay, you're not extracting any work from this system. Okay, so now they're asking you to look at the other extreme where you make this heat transfer reversible. So we want heat exchange with addition of some Carnot engines and Carnot refrigerators. So that we have seen in the lecture class also. So if you do this, you might be able to manage reversible heat transfer. Okay, and if you want to make a connection to practical scenario, then yes, it won't be a fully reversible operation in the sense that you will not get delta S total to be zero because you don't have a Carnot engine or a Carnot refrigerator in reality. But you can the inefficiency. Okay, so that is the only thing you can do. You cannot make inefficiency zero, you cannot make lost work zero, but you can make it smaller. Okay, now our design involves putting a heat engine, furnace, and the house. Okay, so for example, this is, and again you can compare it to other processes. For example, throttling, you go from high pressure to low pressure without obtaining any work. Okay, so in some sense again you are wasting resources. Okay, so if I take example of throttle, then if I look at a Mercedes high-end car, they are using CO2 as a working fluid, and they have replaced throttle by a device which can produce work. Okay, so they call it a turbo expander. So something like that we are seeing here also. Okay, so putting a heat engine between two reservoirs, one at high temperature TF, other which is my house at temperature T. Now we use the work produced by this heat engine to drive a refrigerator which is able to move the heat from low temperature. So I have surroundings, which is the outside of the house at some low temperature, maybe 0 degrees Celsius. Okay, and let's say I want to maintain the house at 298 Kelvin, 25 degrees Celsius. Okay, so we use the work obtained from this furnace to drive a refrigerator. You can put now the Q values. The heat extracted from the furnace, let's say, is QF. Heat added to the house from the top side is Q1. Heat added to the house from the bottom side is Q2. Heat extracted from the surroundings is, let's say, Q sigma. So these are all my individual numbers. And the condition, one constraint is the total heat added to the house is the same as the irreversible case. Total heat added is still Q, but now we are doing it via a different route. Okay. Black box of sorts, you will see house is still getting the same net input of heat. So we have not changed that design element. Okay. Now to obtain my unknown quantities, I will combine the first law and the second law. So this is the net heat added. Sorry. Yes. So this will also be fine because the work term from engine is cancelling the work term from the refrigerator. So you will get QF plus Q sigma equal to Q. So that is my first equation. Then you put the second law because the process is reversible. So the total entropy change must be zero. So you have a reservoir, which is house, another is reservoir, which is furnace, from which you are removing heat. So therefore the minus sign. One more reservoir, which is the surroundings, from which again you are removing heat. So again the minus sign. In the house, you added heat, so the plus sign. So this is your second law. And now you can just combine these two equations and obtain the unknown. Okay. Again, there is not one way to solve this problem. You could have used the first law and second law individually on engine and refrigerator. It will increase the maths, but of course you will come up with the same answer. Right? Any queries? Problem 5.10 is somewhat similar to what we did in the lecture class, as well as one of the papers which I shared. So it is asking you to look at heat exchangers, two different operations. Co-current, where both the streams are flowing in the same direction, the hot and cold. Counter current, where the two streams are flowing in the opposite directions. Okay. They're asking us to calculate the total as well as, so for total, I need to know individually for each stream. Okay. And here there is no exchange with the surroundings. So the total entropy change would be just the sum of entropy changes for the two flow streams. Okay. So for both of these, given the assumption they have told me Cp is constant, for heat exchanger operations, I can assume roughly constant pressure operation. There is a pressure change, but it's not significant typically. Okay. Otherwise, you have to use the more general expression. All right. So if it's a liquid, you are okay with ignoring entropy dependence on pressure for small changes in pressure. 5-10 bar change in pressure, even 20 bar change in pressure will not matter. If the flowing streams are gaseous, then you will need to include pressure dependence also, because for gases, properties are dependent both on pressure and temperature kind of equally. All right. So this is the formula you will use. And the total entropy change would be just the sum. And this you can obtain from the entropy balance equation also. So here I'm writing it directly, but you can obtain it from the entropy balance equation also. Okay, so Sg naught, if you want to calculate, it will again come out to be the total entropy change for the flow streams in this case. So for case A, given the numbers, this is what you will get. Clearly you can see process is irreversible. Inlet temperature of the hot stream is changed from 320, I believe, to 200 degrees Celsius. And still the same delta T is obtained for the cold stream. The inlet temperature of the hot stream, I have decreased it, but I'm obtaining the same temperature change for the cold stream. So what needs to happen?
Total entropy change is 0.
No. The process is still irreversible.
अच्छा irreversible है.
But the question is that I have decreased the inlet temperature of the hot stream. I have not changed the inlet and outlet temperatures of the cold stream. I have not changed the flow rate of the cold stream. So what needs to happen so that all these constraints are met? You will need to change the mass or molar flow rate of the hot stream. So this kind of refers to the paper I have shared. Section. Okay, so let us see right now, because we are not going to look at fluid dynamic aspect. So you will see change decreases. So if you do the calculation again, the total entropy change in this case is going to become smaller, right? So you can clearly see that if I only had thermodynamics only on TP, T2, T1, etc., right? So if I was only consider this aspect of irreversibility, what you are going to see is it makes sense to continuously decrease delta TH and continuously increase MH naught, because doing this will make sure that delta is total. That means the process inefficiency is as small as possible. However, as discussed in the lecture class, as we increase the mass flow rate, viscous effects, viscous friction effects. Okay, so think of a pipe flow. If you're going to higher flow rates, frictional losses are larger. So those frictional effects or frictional losses will tend to increase. They also contribute to SG naught, which we have not discussed in this course at all, but that paper I have shared discusses. Okay, so this flow friction effect increases, and therefore this other contribution to the entropy change, which we have so far ignored, at high mass flow rates we cannot ignore it, and therefore there will be an optimal flow rate at which the process inefficiency is minimal. Okay, so if I only look at, we keep decreasing the inlet hot stream temperature, keep increasing flow rate, and you will improve process efficiency. However, that is not the case. Okay. Any questions? Five 5.29 is essentially an example of the working of a vortex tube. So of course, the vortex tube doesn't look like this. So we are just putting a box around the vortex tube. It involves an inlet of a compressed stream, room temperature, and as an outlet, it gives me a hot stream and a cold stream. Okay, so without any refrigerator, without any engine, just by using a compressed stream, I'm able to obtain a stream which was above the temperature of the inlet and another stream which is below the temperature of the inlet, right? So I can use it in processes where I cannot easily put heat engines or refrigerators, and I still want heating or cooling. Okay, so that is one means, and that is why it is used in industry. Section of hot stream is eta H or NH, whatever you want to call it, and the cold will be 1 minus N. Okay, so we are having one, let's say 1 mole of inlet, eta is hot, 1 minus eta is cold. Okay, so typical use of this kind of setup is in spot cooling applications, okay, where you don't have a very large heat or cooling requirement, but you are restricted in space. This will be a very nice setup to be used there. Okay, so the question they are asking you is how much cold stream you are getting per hot stream at the outlet, or you can say how much cold stream you are getting per mole of inlet stream, whatever way you want to ask it. Okay, so this answer you can get by simply applying the general energy balance. Okay, and what you will obtain is processes adiabatic, no moving parts, etc., etc. So standard assumptions which we are taking. So this is the equation you will end up getting, and now delta H equal to 0. Second part they are asking is, all right, you have designed this process, but is it feasible? The feasibility check in thermodynamics at least requires you to calculate the total entropy change. If it is not violating the second law, it is going to be feasible. So you calculate the total entropy change, all the numbers are given, and you would indeed find that the total entropy change is positive. That means the process is feasible. Okay, any queries? All right. So this 5.29 in a way gives you the thought process you have to take up when designing a new system. You ask what endpoints you want, what initial points you have, visibility, it reversible process that gives you the best you can get. Of course, whether you can do it or not, and secondly, how much, what is the cost? Okay, what is the inefficiency? And then you can go to the next step, which is actually designing the process. 5.39 gives you an example of a turbine. Which is producing some work. So this is an adiabatic expansion process. So these are the given details, okay? And the process is given to be irreversible. Again, right now we are restricted to using ideal gas as a working fluid. Chapter 6, Chapter 7, we will use real gas as a working fluid, and we'll talk in much more detail how to design turbines, okay? So we are going to see just you can say initial aspects of that, but much more detailed analysis on turbine design in terms of inlet conditions, outlet pressure. We'll talk about that once we get to chapter 6, chapter 7, where we can go to real fluids. For example, one very standard fluid which is used in turbine applications is steam. Okay, so water, steam. So we'll discuss how to design a turbine with water as a working fluid or with steam as a working fluid. So you apply the general energy balance. So this is something which you have already done in chapter 2. And the work output from the turbine, you will be able to write in terms of enthalpy changes only. Okay, so I'm just using the standard approximation which we have done earlier also. Now they're asking you to compare this actual process against the so-called ideal process. So we have defined the ideal process as a process with same of state but carried out reversibly. Okay, that is how we have defined our ideal process. And this efficiency which comes out is known as thermodynamic efficiency. Another kind of efficiency which is typically defined for turbines. So if you go to the market and look at the turbine data sheet, sometimes you will see the word isentropic efficiency is mentioned rather than the thermodynamic efficiency. Okay. And the reason is for turbines, same endpoint as reversible process is not required. Okay, so therefore it does not form the correct comparison aspect. So the end state exactly is not required to me. Rather, I have a constraint on the exit pressure. So on the inlet, I have constraint on P and T, that this is P and T I am working with. However, on the outlet, I am not so much concerned about the temperature at the outlet. Rather, I am only concerned about the pressure at the outlet. Okay. So we define the comparison point as adiabatic reversible process with same exit pressure. Okay, and adiabatic reversible means isentropic. So that is why we call this kind of efficiency as isentropic efficiency. Okay. So you can try to do it for both cases. So your actual process is adiabatic and irreversible. Now let us look at the ideal process as per the thermodynamic efficiency state. So that means same change in state. The process I can say is reversible, that is a requirement. Further, I can say for sure the process is non-adiabatic also. This I'm leaving to you to show that indeed that would be the case. Okay, so if I'm comparing an adiabatic irreversible process, so this I've actually discussed at the very beginning of this tutorial. So I'm comparing an adiabatic irreversible process against an reversible process. Okay, so here the comparison is between adiabatic reversible, between the same endpoints. These three things say for sure that that means the ideal process would be non-adiabatic. Okay, so this I'm leaving to you. In terms of calculation, all the equations have been given. For example, for the ideal process, the work done we have stated. For the case of single flow in, single flow out, steady state, steady flow operation, etc., this is what you end up getting. Okay. So the numbers I will give you so that you can check your calculation. The actual work comes out to be 3753. Ideal work would be larger or smaller, magnitude wise? Larger. The lost work is the difference between the two. The thermodynamic efficiency, because W is less than 0. This is how we'll define it. And the reason we are defining it this way is we want the efficiency to appeal to our intuition. The definition of efficiency should appeal to our intuition. It should be less than 1. Okay. So this we have discussed in the lecture class. If W is less than 0, this is the definition. If the work is positive, the numerator and denominator are inverted. Okay. Any questions? So 5.45 is again looking at the turbine, and the analysis of this problem would come in very handy when I talk about design of a turbine to improve its efficiency. Okay. At this point, the analysis is simple. They're talking about two possible endpoints, 2 and 2 prime. 2 is the actual endpoint, and 2 prime is in the ideal case, ideal isentropic case. Okay, so this is the other aspect which I talked about just now, that for turbines, rather than talking about thermodynamic efficiency, we rather talk about isentropic efficiency. So both the processes now, 2 and 2 prime, are adiabatic. Irreversible process because that is the actual process. 2 prime is our reference process, which is the reversible process. Okay, so those are the details which are given to us. Let us draw it on the PV diagram. And all I will do later on when talking about real fluids, I will also put in the background the phase diagram. And you will see by putting the phase diagram in the background, our understanding of the entire process, our understanding of the design of this process will improve significantly. So inlet is fixed, okay? At the outlet, so P2 is equal to P2 prime. However, the temperature and by extension, the volume is not fixed. Yes, I am going from 1 to 2. And in other case, I'm going from 1 to 2 prime. Okay, so the location of 2 and 2 prime, I have actually drawn after solving the problem. What they are asking in the problem, they are asking us to outlet temperatures. Okay, so is the outlet temperature in the ideal process equal greater actual process? So that's what they are asking us to do. All right, so let us see how to do it. I know that for the reversible process, entropy change would be 0. Okay, and for the irreversible process, it would be positive. Why I am writing down the second law in terms of system only? It is applicable to the total entropy change. But here I have written the second law for the system only. Why?
Because it is adiabatic.
And therefore,
Therefore, surrounding del S surrounding becomes 0.
perfect. So entropy change of surroundings is 0. Therefore, the second law is reduced from entropy change only. All right. Now we already know how to calculate the entropy changes for the system. So for the irreversible case, because now the working fluid is a gas, therefore I will need to include both temperature and pressure effects. And I'm taking the gas to be an ideal gas. For the reversible, temperature change is from T1 to T2 prime. The second term is the same as the irreversible part. Okay. And now you take the difference of the two, delta delta S. Looking at these highlighted things, you can see that this quantity must be positive because irreversible is positive, reversible is 0. And from the maths, I can find out the expression for delta delta S. And from here, I can conclude if this quantity needs to be positive. So the entire thing we have reduced to this last boxed equation. If this is the case, can only happen if T2 is greater than T2 prime. The maths proof I leave to you. So why I can say this convincingly without any doubt. What are the requirements on the integrand? Which ensures that I can indeed say T2 must be greater than T2 prime. Anyone wants to tell it now? Or maybe you look later, go to your high school maths, find out why this is true. All right, so that's all from my side on chapter 5. And now we have several minutes left. If you have any queries, any questions on this chapter or chapters before, you can ask.
Sir, I guess CP ln T2 by T2 T2 dash will come on integration. So
If you
that
take CP constant, then yes, it becomes easy, right? You don't need any theorem. But if CP is not constant, it's a function of temperature. Then what are the requirements on the integrand? So you're right. If I take CP to be constant, then it's very easily seen mathematically that ln T2 by T2 prime is coming out to be positive. So therefore, T2 above T2 prime, right? But what if CP is a function of temperature? Then what are the requirements?
So then also CP and T would always be positive. So
So all I'm asking you here is state it in
अच्छा,
a precise mathematical way. I have no doubt that this is true. All I'm saying, asking you is state it in a very specific mathematical theorem way. All right. Yeah. Any other? So you don't have to do it right now. Okay, but it's just a
sir,
side question.
are we supposed to use the equation for gases that A plus BT plus CT square plus DT D by T square? That one for CP.
No, no, no. I mean, yes, you can use it, but then again, you get a different kind of math answer. So here I'm asking you to prove the generality of this thing. What are the general required? Because that is again a specific formula for CP. CP equal to constant is a specific formula. CP equal to A plus BT plus CT square plus D by T something is again a specific formula.
So, sir,
So, but I'm asking,
general requirement
yeah,
for CP we are considering. What should be
CP by
the?
T, the integrand.
Okay, okay, I got it. I got it. What
Right.
should
So
be
what are the
that?
general requirements for the integrand for this to be always true?
Okay, okay, I got it.
Yeah. So any other queries from previous problem sheets or any query from the lectures, please feel free to ask.
Sir, I had a doubt from lecture 5, wherein
Mhm.
we're discussing the PV phase diagram. So you had said that when P greater than P saturated, then T is less than T saturated. But this was not evident from the graph. So how are we concluding for the temperature that T is
It
less
was
than T?
for it was taken from PV graph, PV diagram. Consider the PV diagram.
I was not able to visualize it properly. That how we have
Okay.
taken.
Yeah. Let's go. So tell me which lecture you said?
So lecture 5.
5. This would be in here, right? Somewhere.
Yes, sir. Here.
Okay. So somewhere here I was saying it, right? So better would be to visualize it from PT diagram. And this shows you the vaporization curve, right? So here I'm not drawing the entire PV diagram. Okay, just the liquid and vapor states. All right. And tell me if we are looking at P greater than P set, the points which are
Yes.
P greater than P set. Okay.
Yes.
So that becomes something like this, right? So this point is at P1 T1. Okay. So if I want to talk in terms of pressure, okay, then I would compare this against P set at T1. Okay. So you can see P1 is greater than the saturation pressure at this temperature. Okay. Now, the other way to visualize this would be, of course, that you fix the pressure and compare against the saturation temperature at the given pressure. So you can see by that route, actual temperature is less than the corresponding saturation temperature. Okay, so to give either of these two statements, I need to either fix the pressure and then ask what is happening to temperature, or fix the temperature and ask what is happening to pressure. Okay,
Yes, sir. Understood.
it clarifies now.
Yes, sir.
All right.
And so one trivial doubt that if two bodies have same temperature, then is it the sufficient condition to say that they are in thermal equilibrium? Like what?
Yes. So that is. However, what I will also say is they need to be in thermal contact. So if you recall, when discussing these concepts, I talked about two chambers which might be separated by an adiabatic partition.
Yes, sir.
Okay. So the concept of thermal equilibrium or any equilibrium, mechanical equilibrium or reaction equilibrium, is valid only if there is a possibility for that gradient. So if they are not in thermal contact, then even if they are at constant temperature, I will not say them they are in thermal equilibrium. You go back to the zeroth law of thermodynamics. Let's see if it's here. Yes, right. So that was our definition of thermodynamic equilibrium. It categorically stated object 2 is in thermal contact with object 3. So if there is no thermal contact, there is no concept of thermal equilibrium.
Okay, sir.
Okay. Other questions from the problem sheets or from the lectures or anything else? So we can close the class. Okay.
So,
Yeah, please go ahead.
in that question of HVAC system,
Mhm.
can we use that engine refrigerator combination which we discussed in last lecture, last slide?
I mean, that's what we are doing here, right? In a way.
I mean, in that system, we would be taking the refrigerator would be taking up heat from the house and giving it to the outside.
You mean I don't need the furnace at all?
No, not the furnace, the T sigma thing. That part, the lower
Yeah.
part
Okay.
of.
So, okay, understood. So see there. Uh, house at T. So you're saying essentially if this is the scenario, right? And I believe there was some other temperature there also, and then you had surroundings, something like this, right? Not fully sure if that was a drawing, or you can have T sigma here and you can have TF here. Maybe that would be exactly what we are doing in this case, I believe. So you are putting heat from the furnace. And, all right. So what do we want here?
T sigma, is it
I
a
think
symbol?
easiest could be maybe we actually make this as TF. This could be your house. So now these arrows are pointing in this direction. And now from the house, you want to add heat to the house also, I believe. And because the surroundings are at a lower temperature than the house, so this needs to be a refrigerator. And you are using the work obtained from the engine to drive this refrigerator. So this is basically what we do in the lecture class, right?
Achha, we are also putting heat from the surroundings to the house. Okay.
Yes, yes, yes. Here, that's what we're doing here, right? Q2 is coming from the surroundings to the house. That is why you are able to reduce QF, right? So surroundings, then you were putting QF or QF was equal to Q. So whatever heat requirement was for the house, entirely it was being met by the furnace irreversibly. Now a part of the heat is being added from the surroundings also, and therefore, yes, you are extracting less heat. And if you are extracting less heat from the furnace, what is the meaning of that? You are burning less fuel in the furnace.
Yes.
Okay, so that is my saving here. I'm burning less fuel in the furnace. Okay, so the drawing in the right is exactly what I believe, similar to what I believe drew in the only difference is there we were getting net work output from the process. Here, my concern was not net work output, but rather to decrease the fuel requirement in the furnace. So, therefore, whatever work is being generated from the top part is being used to drive the bottom part, the refrigerator. So, I'm using that obtained work fully to drive a refrigerator because here I'm not interested in extracting work. But if you go to that Mercedes car example I gave, there that's what they're exactly doing. They are extracting work by converting an irreversible throttle process with zero output to a work output in a turbo expander. So it just depends on what is the end goal here. Okay, here the end goal is decrease the fuel consumption of the furnace.
Yes, sir.
Okay, anything else? Okay, so I believe we should have minor exam every week. That way the attendance could be higher in the classes. Let's stop recording.